So, good morning, everyone. Thank you so much for joining us. This session is FRC log replay and simulation, taking the next step. And for anyone who's just joining us, we'll reintroduce ourselves. My name is Jonah. I am a software mentor for Team 6328, and I'm also a core developer for WPI Lab.
My name is Neil. I'm a junior on 6328. I'm a fourth-year software student, and I don't have a third favorite color.
Okay, so here's what we're going to be talking about today. Starting out with talking about what is simulation. We'll go through some different simulation architectures. We'll talk about what AdvantageKit is with several case studies. We'll talk about modifying the past, and then some discussion of AdvantageKit's template projects. And finally, we'll talk about what is the next step. So for anyone who might have seen this presentation before, we included some case studies and use cases you might not have seen before, so we hope that that is informative. Okay, so to start out, I'll say this presentation is a little bit different than the last one, for those of you that saw that. And before we start, I want you to take a moment to think about what your goals are in watching this, and what do you hope to take away? So for most of you, we expect that you'll hopefully see some interesting ideas and see some of what's possible in FRC software. Even without implementing what we talk about today, you might get some new ideas or things to think about. Now, we expect that for few of you, you might go on to actually implement some of what we're going to talk about today. And for you, this presentation is really just a taster. We would highly recommend checking the documentation, asking more questions, etc. But the advice and tools that we're sharing right now are going to be targeted at those of you who are really excited to work through complex problems on your own. This is the next step up from what we talked about in the last session. We are very much straying from the beaten path here, so you've been warned. And make sure you're thinking throughout this presentation about your team's needs. Okay.
So in the broadest terms, when we talk about robot simulation, we're talking about testing code without a physical robot. Of course, this has a bunch of use cases. The first one might be that we get to develop code while the robot is still unfinished, and we can get a head start on software before we get to test it out on the physical robot. This allows us to maximize our time when we have access to the robot, because of course the people who are building the robot like to spend time building the robot. So at home or at competitions, time's really valuable. And so anytime that we get to refine a robot code when we don't have the robot available, so we have the proper code running when we have access to it, is really important. And simulation allows us to help out or work out the simple issues ahead of time, so that when we're working with the real robot, the only things that we're working on are tuning and minor adjustments just to make it work on the real one. Also, at competitions, we have an opportunity to do rapid debugging. Of course, not everyone has access to a practice field 24/7. In fact, we have it maybe like less than 1/7. So after pits close, for example, we can't use the physical robot. And so changes we want to make in our auto and some of our sequencing has to be done in simulation, and then we can test it out the next day. So simulation allows debugging to continue and allows changes to be made. So how does simulation actually work, though? So especially coming from industry, simulation can mean a lot of different things. So the way we mean it is that it means running code on a laptop, for example, without a RoboRio or any of the hardware that would come with the robot, as well as native dependencies such as WPI Lib and other vendors. And WPI Lib has a great set of tools to allow this to work with your team. It also means using simulated hardware. If you don't have an actual CAN bus, PWM outputs that would be on the robot, we need some way to make the code function without using it. Also, we simulate a physical environment. For example, on the picture you see here, this was in 2020 when we were testing a physics simulator for the whole robot. And here there's just a full physics environment with the robot code and the robot that it can interact with. And industry usually covers all three levels of this. We found that in FRC, we can typically rely on the first two, and we'll still get amazing results for our standards. So rather than a single physical environment, we usually use separate individual environments for each subsystem, so we can make sure each one is working as intended, and then we can figure out the whole harmony of the orchestra with some other adjustments that we don't need using simulation. So here's what that looks like. Rather than using one single simulated environment, in FRC we usually give each subsystem its own physics simulator, and the benefit of this is that each simulator is a lot simpler. WPI Lib provides classes for all of these examples, such as a drive, a flywheel, and an arm, And when we apply voltage or current, we can see how the subsystem moves in accordance with its own logic. The downside is, of course, that we can't simulate interactions between each physics simulator running for each subsystem. But usually this isn't a problem in FRC because the only contact that we care about is usually within the same subsystem. And even for more complex subsystems, such as a double-jointed arm, we can just make a slightly more complex physics sim for that specific subsystem rather than having to worry about everything working together. So before we get too deep, let's talk about one example of this where this was useful. In 2023, we successfully built a triple-jointed arm on our robot. And software, of course, was a big challenge to make everything work together, so we had to start early. So the way we got this done was, of course, through simulation. So this is our 2023 robot, and before writing code to control it on our own, we needed sim to make sure the robot didn't break itself when we started debugging on the actual thing. So we implemented a physics model for the double-jointed arm, and this is what that looked like. And we can see that the joints are interacting realistically. They're slowing down, speeding up with gravity, with how the motors are being used by the logic. It also goes to the floor. So, of course, it doesn't interact with the ground. It has its own physics sim. And that's the downside of not having one physics sim for the whole thing. But, I mean, with a simple eye test, we can see that that wouldn't actually happen on the real robot. And, of course, when we're powering it, that's probably not going to happen anyway. So now we got to work writing the actual code to control the arm. These are just a few visualizations of how some of that original code was written. And then when we actually wanted to simulate it, when we had the code ready, we were able to transition to the 3D view, where we could see the robot move around. It's running all the trajectories, the feed-forward model, the PID controllers, etc. One question you may ask is, did this perfectly match the real robot? And of course, the answer has to be a no, because the simulation we made was before the design was actually finalized, so the inertia, the gearings, aren't quite exactly right. But I think for FRC, that's completely fine. The more important thing is that we had the general concept down so that we could work on the tuning and all that stuff on our own with the physical robot. This is the main architecture and archetype of the robot, and we had it working down. Of course, some communication with the mechanical team is required to make sure that the general high-level goals are the same for the sub-teams, but I think that's possible for most of our teams. And making a one-to-one between the physics sim and real life is just, it's kind of a rabbit hole, making everything perfect. And in that time that you spend, things are going to change anyway. There's so many variables that you have to control. So it's a lot nicer to just stick with this, because this works for FRC, at least for our team. So here it is on the real robot. Another detail that we had to do was keeping track of all the constants that are running on this robot versus in the sim. So it's as simple as just keeping different constants for when we're simulating the robot in AdvantageKit versus when we're actually running the robot with the real physical motors. We just store two sets of gains, and we can do more if we have multiple robots that we run in real life, such as a dev bot and a comp bot, maybe a kit bot, and all that fun stuff. So everything can be tuned separately with no problems.
Okay, so all of that is good at a high level, but you might ask, how does that actually work? How is that implemented? Well, the core of the simulation is the physics model, and remember that in this case we're talking about each subsystem individually. WPILib provides a whole bunch of built-in physics models. You can see some of them there. And all of these models take in a voltage and they output a predicted subsystem state, like your position and velocity of an arm. That's all based on a simplified model of how the subsystem works, but it's a decent approximation. Now, even if we can simulate the movement of each subsystem, how do we actually use that data? Well, so your subsystems probably look something like this. You have subsystem code that's talking to probably a CAN-based motor controller. So you're sending commands to the controller and reading sensor values back from it. So where does physics simulation fit into that? Well, the first technique to solve this problem is called data injection. This requires support from the vendor, and what they'll do is provide a sim object, which is connected to the real controller internally in their vendor dep. You can then read the applied output back from the sim object. You run your physics simulator within the subsystem, and then the simulated sensor outputs are written back to the sim object. Then those simulated outputs can be read back through the normal object, through the standards interface. This is the structure that's generally recommended by WPILib and by most vendors, at least those that support it. But it's not the only way. One alternative, which is what we're going to focus on, is called hardware abstraction. And with hardware abstraction, subsystems look something like this. In addition to the core subsystem, you also define what we call an I/O interface. That contains methods for all of the inputs and outputs of your subsystem. So think methods like set voltage, get position. And the nice thing now is this I/O interface can have multiple implementations. For example, we might have a real implementation that uses the motor controller object from a vendor, but we can also have a sim implementation that runs a WPI-lib physics sim without using the vendor dep at all. We can even swap out these implementations or have multiple real implementations for different vendors, for example. Now, both of these architectures have benefits, so let's compare them. First of all, with data injection, you get the benefit of vendor control loops. You can easily simulate onboard controllers if you're running your PID controller on, say, a Talon or a Spark Max rather than the Rio. Some vendors also support high-fidelity CAN simulation, where it will simulate the timing of CAN frames on the bus. And it allows you to write a single-class subsystem, so everything is in the same place. The downsides is that, first of all, it has a fairly convoluted data flow. We find it's fairly easy to mix up how data is supposed to move around here when you're reading and writing inputs from multiple different places. And it's really easy to accidentally read, say, simulated outputs when you were supposed to read them from the main controller. So now you have code that works in sim, but doesn't work on the real robot, which largely defeats the point. Another downside with data injection is vendor lock-in. It's not supported by every vendor, and it ties you to a single vendor at the start of the season, rather than the one that might be best for your needs. So what about hardware abstraction? Well, a major benefit is that it's a much simpler data flow. It's easy to explain, and we find it's much easier for most students to understand. It's also easy to break down. So we find that for a lot of students, when jumping into writing code, it's very nice when they only have to think about one interface or one implementation with a defined role, rather than needing to deal with everything all at once. It also enables vendor flexibility. Your simulation isn't tied to a vendor at all, and you can have multiple real implementations. So for example, for the past 2 years, our development robots have largely been based on the Spark Max and Spark Flex, while our competition robots are using CTRE's ecosystem. And we can support that really easily with hardware abstraction. The major downside of hardware abstraction is that the vendor simulation is lower fidelity. So if you're using a complex vendor control loop like Motion Magic for CTRE, you might need to recreate that yourself using, in this case, a profiled PID controller. Generally, that's not too difficult. It's very doable for any vendor feature you might want to utilize. And it generally doesn't matter as much either if you aren't trying to perfectly match the simulation to the real robot, like Neil talked about. Now, which of these is the right choice? That depends on your team and what you're doing in sim. 6328 has used hardware abstraction for years. We've never looked back. It's worked really well for us. But there's also another reason we like hardware abstraction. And to get to that, you might have noticed this presentation is called Log, Replay, and Simulation. And thus far, we have only talked about simulation. So we're going to switch gears for a moment, and we'll come back to hardware abstraction. So log replay is where a library called AdvantageKit comes in. Physics simulation, which is what we've been discussing since the start of the presentation, is what we recommend to most teams. AdvantageKit is really taking that step beyond normal physics simulation. And it may seem unrelated at first, but these things will be connected together shortly. Now, for those of you who didn't see our last presentation, here are the 3 levels of logging we talked about. There's driver station logging, onboard logging, and log replay. We talked about levels 1 and 2 in our last presentation, and we're going to focus on level 3 here. Now, this is what we might refer to as log everything. A log everything framework. The idea is that we want the full internal state of the robot code to be accessible using a log file. This means that there is no risk of not logging a field. Now, it is more complex to implement than level 1 or 2 logging, which is why we don't recommend it as broadly. But it is very much doable. And there are several tools available to help with that, including non-FRC frameworks like FRC. Now, we're going to focus on AdvantageKit for this presentation. And before we get too much further, I do want to note there are other tools which are advertised as supporting log replay, even though they might have very different capabilities. We're going to try to be precise in our terminology here to avoid confusion. So when we're talking about log replay, what we're specifically referring to is what we might call deterministic log replay. You'll see what that means in a moment and why that's important. AdvantageKit is currently the only library in FRC that supports deterministic log replay. So all of these case studies will be utilizing that. Okay, so to understand what's going on with level 3 logging, we're going to simplify our view of the robot code here. Now fundamentally, what robot code is doing is it's reading a set of inputs and producing a set of outputs. Inputs are things like your encoder values, your joystick inputs, your enabled state, other sensors, etc. Your robot code is a bunch of internal logic. That would be your subsystems and your commands and your controllers. And it's outputting things like motor voltages, pneumatic commands, or your odometry pose. And notice that we would consider something like odometry pose an output in this example, even though it's used in other calculations. It's something that the robot code is producing from the inputs. Now, with this model, here's what level 2 logging looks like. We're going to sample a few key fields from the inputs and the outputs, maybe the joystick values for the driver controller, plus the odometry pose. But of course, we can't look at any of the fields that we didn't choose to log ahead of time. And to fix that, here's what level 3 logging is going to look like. Let's break down what's going on here. Instead of logging just a few select fields, what we're going to do is log every input field. That's really important. Any data that the robot code is using is going to be logged, regardless of the source of that data. But why would we want to do that? Well, what we can do is run the same robot code in a simulator and replay the inputs from the log file. And when we do that, the code is going to do exactly the same thing as on the real robot. That's kind of a wild idea. Feel free to take a moment to wrap your head around that. But the idea is if we take the same code and we give it the same inputs in the same order, it will always give us the same output. It is deterministic. What that means is that we can measure all of the outputs from our simulated code and be guaranteed that they are the same as they would have been on the real robot. We can even adjust the code to generate more outputs than the first time around. So we can log outputs that we never included in the log file in the first place. That's all really great in theory. Let's talk about how it changes things in the robot code. AdvantageKit needs to be able to log and replay all of the code's input data. Some of that data is managed automatically by AdvantageKit. That includes the robot state, joystick data, dashboard inputs, etc. And it's also worth noting that timestamps are included in that list. AdvantageKit is guaranteeing that all timestamps read during a single cycle are identical so that they can be replayed accurately. AdvantageKit produces what we call timestamp synchronized logs, which means that all the fields are updated once per loop cycle, and each loop cycle has a single timestamp. In order to guarantee, Now, the other side of this are any inputs that are part of subsystems that aren't handled automatically by AdvantageKit. That might include your encoders, gyros, limit switches, things like that. And that's where hardware abstraction comes into play. Now, the I/O interface defines the input data for the subsystem. When running on the robot, AdvantageKit will record all of the input data from the I/O layer. And then the fun bit is when running in log replay, we just turn off the I/O implementation, and AdvantageKit will provide all of that data instead. So the subsystem, and in fact the rest of the code, can't tell the difference between real hardware and the replayed log. So you still get all of the benefits of the hardware abstraction too. You can write a physics simulator implementation, for example. Now it's worth noting here that simulation can actually mean two different things in an AdvantageKit context. It can mean physics simulation, like we talked about earlier, where the states of the mechanisms are simulated based on simple models. Or simulation can mean that log replay is happening, where the states of mechanisms are based on a log file, and that's running with no I/O implementation, as opposed to a simulated one. Now, if you're curious for more details about what the code for all of this looks like, I'd encourage you to check the AdvantageKit documentation. There's lots of examples, much more in depth than we're able to cover here, and that'll be linked at the end of the presentation too.
Yeah, so that was a lot of the what, and now hopefully we'll get into a lot of the when and the why we used all of this. So this is our first example is when we were using log replay to generate extra outputs from a log file that weren't logged at the time of what code was running. And we can take a look at one of our log files from earlier this year. And here you can see the height of the elevator over time. And we can add the set point position overlaid. And based on a trapezoidal profile, which will limit the velocity and acceleration, we'll get that set point. That's how the elevator works in our robot. And you can see that tracking seems to be working pretty well, but that's only part of what we would be realistically outputting in a real match. Another thing is that each of these intermediate set points has both a position and a velocity. So this is the position. The other thing that we could track is the velocity, because we want to be sure that the feed forward that's running on the elevator is working properly. So we can switch to a graph of measured elevator velocity here. And we can see the velocity is changing when we're driving to the set point. But there's an important piece of the puzzle that's missing, which is the set point for the velocities. So we saw that earlier that we are logging the set point for the position, but unfortunately, at the time of this event, we weren't actually logging the velocity set point. So like the profile set points that are ultimately given are because of the joystick inputs, sensor values, all these inputs. And all of those inputs are then logged, so then we can go back and change how, what the robot is logging, so we can create more new outputs using AdvantageKit. Except there is one problem. So if we return to our diagram here, we said that the simulated robot code will behave exactly the same as long as the original robot code receives the same inputs. Here we have two conditions. We have the same inputs, but the other thing is that we need to be running the same code. It must be identical. So we can look at the log, which is from earlier this year, and our 2022 robot code changed a lot during the off-season. So our robot code was, of course, checked in with Git, so we can check the commit hash to see what code was running on the robot at this time. So commits don't include any uncommitted changes, so the way that we've gotten around that for competitions where it's a lot more fast-paced and we want to know what's running on the robot every time we run it, is that we have a Gradle task that automatically generates a commit every time we deploy to the robot. So we have all the robot code that's running on the robot every time we're running it. Here's an example commit log from one of our events. We see the timestamp and the Git hash. And these commits are put on an event branch that we later squash in after the event. And so the result is that, of course, we have the code that's running on the robot anytime we'd be playing. So if we go back to the log file, AdvantageKit actually records the metadata from the log, which can include the Git hash. So here we're opening the metadata tab. We can see that it says all changes committed, and we can see the Git hash right there. So we can return to that commit and be guaranteed that we have the original code that was running on the robot at this time. This is our 2025 robot code that's open in VS Code here. And we can see that we checked out the correct commit using Git. We can add a line to record the velocity of the set point. And then afterwards, when we're done with that, we can start the simulation without the GUI. And AdvantageKit will grab the log file from AdvantageScope and we'll simulate it all in like 50 times or 150 times speed, so we don't have to wait the 2 minutes and 30 seconds for all the inputs to be processed through the logic. And we generate a new log file that includes the original inputs plus the new replayed outputs. And the new data automatically appears in AdvantageScope when we open it. And here we can see the set point velocity in purple. And the replay is based, of course, on the raw inputs, the same raw inputs that were logged earlier. But now we have a new output that we generated because of this new code that we're running. And we can see it seems to be tracking pretty well. Another example of how we might want to log additional outputs can be in driving and for vision. So we use April tag localization data, especially in our 2023 robot code, which is for a robot named Banana Split. And the case for this was that we were trying to automatically score all our game pieces because that's just a lot faster. So this video is from an off-season event in fall of 2023, and we'll show a few examples of how the robot looks when everything's working properly. Our robot is in red right now and it has the green LEDs. And you can see the rainbow LEDs when it gets closer to where it's scoring. It's very bright. It might look white on the screen. But essentially, anytime those are running, we know that we're automated, and that's running the auto-scoring sequencing. So in this last example, it'll drive to the position, but it doesn't actually extend the arm. So here we're about to score, and we're in the right position, but our arm doesn't actually extend to put the cone or the cube, whatever we're holding, into the correct scoring position. And we went back to the log. We made sure that it's not a driver error. It's not like they weren't pressing the right button. Everything was fine on that side, so we had to track down the root cause in the software. So let's take a look at how the autoscoring commands actually worked. So at a simplified level, what we have is a trigger that launches the autoscore command, and then we have two parallel commands that are part of this. We have the drive to pose, which takes care of getting the robot to the right place, and we have an arm extension command that's run once we're in the correct threshold, because we don't want to extend the arm before we get to the correct position so we don't get tangled and break our arm. So the conditions for extending our arm is that we have to be within 1.2 meters of the target, within 45 degrees of the target, and 20 centimeters behind the charging station, because we don't want to raise the arm in the middle of the field. We also have a pitch and roll velocities, a bunch of thresholds for that, such as 2.5 degrees for pitch and roll, and our velocities have to be under 5 degrees per second. And this is all because the autoscoring can take a few hard turns when it's automatically driving, so we don't want to tip over, as was very common that year. So when we go back, we can see that one of these conditions wasn't met, which is the reason why we weren't extending our arm. So we can, at this time, we weren't actually logging the states of these conditions, so we had no idea if we were stuck to that version of the robot code, what was happening and what wasn't being met. So we can use AdvantageKit to go back and check. Using log replay, we saw that we can now log all 6 conditions that were being used for the arm extension. And this debugging was actually done on an airplane without access to the physical robot. So again, that's where this type of stuff is really useful. And right here, remember that pink is when it's autoscoring, and we also plotted the elbow and shoulder set points to see when the arm moves. And at the position of the cursor right now, we can see that this is the ideal state, this is how it's supposed to work, and all 6 conditions are true and the arm would move. This is when it fails. Notice right here, the red shows that the pose is intolerance, the purple shows that the pitch is intolerance. But just as we get close, the pitch changes too much, and it stays that way, so we can't extend our arm. If we check the pitch data, we see that our pitch settled at around 2.8 degrees, which is just 0.3 away from our 2.5 tolerance. So what was the cause? Well, we were actually testing our new TPU wheels at this event, and this is an untested one with less stiff spring material between the hub and the tread. So the robot had slightly uneven weight distribution that we weren't as used to, and so one side had compressed more than the other, making us off-center. And this could have been a mysterious fluke that we had no idea what would have happened during this event. We would look back and be like, what? I don't know what happened. So we could now go back and check these conditions, and we have a root cause that we could determine specifically because of AdvantageKit, and because we can go back and retrospectively add new things that we weren't able to see at that time. So of course, to solve the mechanical issue, we can just switch the wheels and all of that.
Okay, so here's one more area where log replay can be helpful. Command-based programming, as you may know, is a very powerful tool, but it's sometimes a little hard to keep track of all of the moving pieces in a large code base. We need to figure out what commands are being scheduled and why, which commands might be canceling or interfering with each other. It can get complicated. So AdvantageKit can help with that. The example here is actually loosely based on a real support request we received from a well-known team during the 2025 build season. So this is very much a real example. They were not using AdvantageKit at the time, but that'll provide a useful opportunity to compare how the debugging process compares with and without log replay. Okay, so what's the issue? Well, this team was trying to run a multi-core auto, and here we're using a simplified example of rather than their actual code, so it'll be a little easier to understand what's happening. Now in this example, they drive forward to score on the reef, and they start a path to the station for their next piece. But here, it just stops. So it looks like the auto is interrupted right after finishing the first piece. So what's going on with that? We can take a look at the code here. Now this is the auto routine that we're running in our simplified version of the code. It uses a number of different subsystems with complex sequencing. And in reality, there were even more layers to this originally, with different command factories and additional abstractions, which makes it harder to understand what's going on. Somehow this command is exiting early, but it's hard to figure out what's causing that to happen. And I said before, this team was not using AdvantageKit at the time, so debugging this was a real challenge. We couldn't recreate the problem in simulation, and we actually ended up trawling through a large part of this enormous competition code base looking for clues. It ended up taking 4 of 6328's experienced programmers more than an hour just to come up with some initial theories of what was happening here. And then even more back and forth was required to actually find and test the fix. So how could that process be improved with log replay? Well, there are a bunch of potential causes to this problem, but a reasonable place to start is to check whether the command is being interrupted, as opposed to becoming stalled, for example. Now, what we're going to do is add some logic in replay to print to the console when the command is interrupted. So right here, we're just going to paste in that code with a finally do decorator, and then launch the simulation with log replay. Okay, and now you can see right here, it prints out a message saying that this command was interrupted. So that's a good starting point, but we want to figure out why was that command interrupted. Maybe it's a conflicting command scheduled from a trigger or a proxy command, but tracking that down is going to be difficult. What we can use log replay to help us track that down. And even for some of you who might have used log replay before, this is an application you may not have utilized to its full potential. It's an interesting application of it. Because VS Code already has sophisticated debugging tools that allow us to examine the execution of the code. And in this new callback function, what we're going to do is add a breakpoint. Let's watch. So we'll add a breakpoint at that line that's executed when the command is interrupted, and then launch the simulation with log replay. Just like before, except VS Code will pause automatically when that line is executed. And it gives us a whole bunch of data. Among other things, you can see here is the call stack of all of the methods that are being run in order to reach this line of code. So who's interrupting the command? Well, we can see right here, these are a bunch of layers of the call stack, which are internal methods in the command scheduler. That's part of WPLib. But at the end here is a reference to the periodic function of the pivot subsystem. We can take a look at that just by clicking on that line, and we jump right to the line of code that triggered this event. And as it turns out, this subsystem included some complex logic for homing its position. So under certain conditions, it would enter a homing mode. And one of the steps before entering that mode is canceling any commands that are running on the subsystem. Since our auto routine requires all of the subsystems on the robot, the result is that we cancel the entire routine, which was probably not what this team expected. And what we just did here is take a problem that originally took 4 of our experienced programmers over an hour to debug, and we solved it in a matter of minutes by jumping directly to the line of code that was an issue. So it makes debugging so much faster when we can examine a problem again and again in simulation this way.
All those examples involve running the same code on the real robot and then replaying it. And that's, of course, the most common use of AdvantageKit is that we can go back and see this stuff. But we can also modify the code to process the inputs differently. When we do that, we do have a few restrictions that we have to think about for how this might be used. So, of course, everything's connected, and if you modify one subsystem, it may affect others in unexpected ways. For example, modifying vision would affect auto-aim, which would affect the flywheels, and et cetera, and it would be a chain of reactions. And this may not match other behavior, and it's generally best to focus on just modifying one part and making sure that works the way you want it to. Here, let's consider the replay bubble. So one good way to visualize what AdvantageKit can do is that we have some parts of the code that can be replayed and some parts that cannot be replayed. And the part that can be replayed can be thought of like a bubble. And any data coming into the bubble needs to be logged by AdvantageKit. These are all of the inputs. Anything outside of the bubble is free to read and write without logging, but it can't be replayed. Subsystems are in the bubble and IO implementations are out of it. When we make modifications, we have to make sure that it only affects the code inside the bubble, which does not include the IO interfaces. Of course, within IO interfaces, there's a lot of nuance. You're free to define IO interfaces however you want. One example is that we might have most subsystems in a cascading set of controls, with the high-level control requests, such as moving a swerve drive forward, being processed through other lower-level control requests, such as moving one module at a time at a certain speed, which might be processed through kinematics, and feedback controllers and PID controllers and all of that. One option is to put the replay boundary here, where you run all your kinematics and feedback loops in the subsystem, and then motor controllers only execute the final commands. And we did this on every subsystem in 2023, and it worked fine for us. Another common option is that we have the PID controllers run on a smart motor controller, and all kinematics happen within the subsystem. And there's also some nuance here. If you're using a profile, you might have to decide whether to run it on the Rio or on the controller. You might have also noticed that our first case study with an elevator profile only works when you're running a trapezoidal profile on the RoboRio. And the structure takes advantage of faster feedback loops, also allowing a lot of the logic to be replayed. And the last option is this, where we would generally recommend against it, but you can use it using some high-level libraries such as Yagsel or CTRE Swerve, which we can talk about a little bit later. And here we have the high-level requests that are replayable, but then everything else is passed off to a vendor library that we cannot really touch. So the upside of this is that it takes advantage of those existing libraries, but the downside is that a lot of the important parts are being handled by something that we can access and it can't be replayed.
So even with all of those restrictions, there's still a lot to be gained by modifying replayed code, and we're going to go through a couple of examples of that. So first of all, in 2024, we were automatically aiming to shoot notes based on the distance to the target, and that required calculating the correct angle for our articulating arm. Now we used a function converting distance to an arm angle, which was just a linear interpolation between measured points. Now, at one of our district events, we found that we ended up shooting from further back than we originally planned. And we were able to hit shots from that distance, but it was way at the far end of our aiming function. And past the farthest point, by default, the linear interpolation will keep the angle constant. It's not ideal to be shooting from so far away past when we characterized, but we should really be able to make a better attempt than just keeping the angle constant. So to begin, we'll plot the points in our map. You can see distance and angle along the two axes, and there's nothing past 4.5 meters to the target. The default behavior with the linear interpolation is to continue the line like this, which is not ideal. To address that, we tried adding one more point to the map, extended out to 8 meters, which is farther than we would ever shoot from, and that's just based on a linear interpolation from the last 2 points. In retrospect, that doesn't work really great either because the angle of the arm would keep changing, and it doesn't really match the pattern of the rest of the points. Okay, so we wanted to confirm the functionality of adding that additional point by modifying code and running in replay. Here, the orange shows the effective distance on the right axis in meters, and right here is the cutoff of our original map. So purple is the original arm angle, and green is the replayed angle where we add in that one extra point. You can see that closer than 4.5 meters, like the example on the right, they match perfectly, but farther than 4.5 meters, the two outputs differ. That's because they're using different functions. The original is constant at 25.6 degrees, which is the angle of the farthest point, and the replay correctly extends the angle further down. That better matches how we would expect the arm to move. But it still doesn't look great. As I said, it doesn't really match the pattern of the rest of the points. So after the event, we made another attempt at this, because we asked, what if we tried fitting a trend line to these points? Well, here's what it would look like if we throw a power function on those points. And in fact, this has a super high R-squared of 0.997. So it's likely to be a pretty good predictor beyond the end of our range. And again, we can confirm the functionality of that function using log replay. Here, purple is our original code, green is replayed. Most of our shots match really well, but when we take a shot from much further away, the power function is able to produce realistic angles. So we switch to this function at future events, knowing that we would be just as accurate from close distances and more accurate from farther distances. Now, another common use case for modifying code in replay is vision tuning. We can change our pose estimation pipeline, which is all inside the replay bubble, and observe the new pose that we get out of this pipeline. Now, one of the features of our 2025 robot is automatic alignment for scoring in the net, which is based on localization data from the onboard cameras. Now, net scoring is a bit of a challenge because there are very few April tags around. And the tags on the barges are directly above the robot when it's aligned to the net, which makes visibility tricky. So let's take a look. This is one of our attempts to auto-align to the net earlier in the season. You can see our robot on the left with the circle there. Let's see. Let's play. Yeah, so we're about to pick up an algae from the reef, and then we're going to swerve around an alliance partner heading to the net. Now, that causes some error in the odometry data, and you can see the robot is not aligned to the net very well at all, and it isn't able to correct fast enough using vision data from that error. So what was happening with the localization data? Well, you can see that visualized to the right, and we're going to replay here. So the ghost robots, the transparent robots, are the individual pose estimates from the cameras. We don't see any tags during this section, and then as we approach the net, we are actually seeing some tags. It's just that it's not updating the estimated pose quickly enough, even though the estimates are quite accurate. So why didn't we trust that incoming data? Well, we actually switched to a new hardware setup this year for vision, which produces more accurate data from a longer range than we're used to. And most of our tuning was based on our previous year's system that was less accurate. So we can use AdvantageKit to test out new tuning for our updated system. Specifically, we wanted to change the way that standard deviations for vision measurements are calculated. We increased the trust in measurements from a large distance, we increased the trust with a large number of tags, and we increased the trust across the board additionally to reflect the overall accuracy improvements in the system. And without needing to test on a real field, we can now see what the estimated pose would have looked like with that new tuning. And in this case, we've hidden the individual vision estimates, but the blue robot, the translucent one, shows the new estimated pose from log replay. This is how the robot would have calculated its position if we had been running this new and improved tuning during the match. So the accuracy, you'll see, is similar as we're swerving across the field in a moment. But as we arrive at the net, you'll see that the replayed pose jumps more quickly towards the vision estimate, so it's more accurate. We can see we're improving our accuracy without significantly improving our noise, which is what we like to see. And this example actually is a good example of the nuance that can come with modifying code in replay. Because in reality, if the robot received the improved pose estimates, it would have driven more forward to correct, which would give it even better visibility of the tags. That's something that can't be modeled directly in log replay, but we can confirm that the basic functionality is correct and know what we need to test on the real field while having more confidence in it. Okay, here's another fun example. We can use log replay to improve our localization algorithms. We've been revising our filtering for several years for April tag localization, and over that time we've developed a variety of different algorithms. We can use log replay to check how much those algorithms are helping us. In this case, the solid robot is our standard pose estimator, and the yellow and red robots are alternative setups that we might be trying out. So we can confirm which of these estimates are more accurate and which of them are jumping around unexpectedly. All of those algorithms come out of just lots of iteration with AdvantageKit in log replay, tuning things using real data from real matches. So AdvantageKit was absolutely essential to us setting up our pose estimation pipeline.
To finish this up, we'd like to quickly discuss AdvantageKit's template projects. We find that a lot of teams might struggle to get started with something like AdvantageKit, and some subsystems might have to be structured in a slightly different way in order to compensate and adjust to this new system. So the template projects are more of a starting point for teams to get started, and then they can personalize it to fit their own personal needs with their own team. So the first template that we do provide is that it's for Spark Swerve, and it's a capable foundation for swerve drives based on the Spark Max or the Spark Flex. It includes all of the advanced features that you would usually see, as well as a default configuration with max swerve. And if you're interested in this, we have more information on the docs available for that. For users in the CTRE system, we also include a Talon FX template project, which we created as an alternative to CTRE's black box swerve library. Since CTRE's code is not compatible with deterministic log replay, we had to create this, so it's designed to offer a similar feature set with full log replay capabilities with a different vendor. And this template is compatible with CTRE's Swerve project generator, and it uses all of the same advanced features that you see listed. And of course, it's fully customizable to your team's needs. Another thing that can be challenging to implement at first is log replay using vision processing. And by correctly logging incoming vision data and retuning the log replay using methods as we showed earlier, we can use AdvantageKit's vision template in order to provide a foundation for pose estimation. And it's fully compatible with all of the other swerve templates that we talked about. It would be something that you add on top of it. And there are several other template projects that are available on the AdvantageKit GitHub. Just look for what your team might use.
Okay, so to finish up, we covered a whole lot of ground. This presentation is called Taking the Next Step, and at the start I asked you to think about your goals at the start. AdvantageKit is very near the limits of what's possible in FRC right now, but that doesn't mean it's the right next step for you. You can consider experimenting with simpler physics sims, try data logging without AdvantageKit, really set up that solid foundation for yourself. And if you find that you're willing and able to stray from the beaten path, as we said, then you can try harder abstraction or AdvantageKit. They're very powerful tools. In general, these are good off-season projects. They're good to experiment with when you have the time. Okay, so here are some links to what we've talked about. Again, you can contact us by emailing us at software@team6328.org. And thank you so much for listening.